So that's our regression equation. Now what can we do with the regression equation? Well, we can use this regression equation to make predictions. So let's do a couple of examples. Let's predict the systolic blood pressure of a person age 55. So in other words, we want to estimate the value of y if x equals 55. And so we're going to plug x equals 55 into our regression equation. Take that times 0.56, add it to 89.4, and we get 120.2. And so we would say that our predicted value of y when x equals 55 is 120.2. And so that explains the significance of this hat. Remember earlier in the semester we always use that hat to indicate an estimate of something. So in this case our estimate of y is 120.2. We denote the estimate by y hat. Now let's do another simple calculation. Predict the systolic blood pressure of a person age 56. So we're going to plug in x equals 56. Take that times 0.56, add 89. We do arithmetic, we get 120.76. So that would be the best predicted blood pressure of a person age 55 based on our data. Or excuse me, age 56. Okay. Now let's make an observation here. When we went from 55 to age 56, the blood pressure increased from 120.2 up to 120.76. So it increased by 0.56. Well, what's significant about 0.56 is that's the value of B1, our slope. And so our slope equals 0.56 indicates that a systolic blood pressure increases by about 0.56 for each 1 year increase in age. So the slope is positive. That indicates that as age increases, systolic blood pressure tends to increase. But the value of the slope is also important. The value of 0.56 indicates that as age increases 1 year, systolic blood pressure increases also by about 0.56. Okay. Now, as we just pointed out, that B naught, as we just calculated, is an estimate of beta naught. B1 is an estimate of beta 1. Beta naught and beta 1 are values from the population. We're never going to know those values exactly. B naught and B1 are point estimates of those population values. So we could think of these beta values as like parameters. B naught and B1 are point estimates. Well, like we did in Chapter 7, whenever we tried to estimate a population parameter using a point estimate, we want a measure of its accuracy. Do that using a margin of error and confidence intervals. Well, in the output from Excel, we get confidence intervals for the values of beta naught and beta 1. And those are given in an output that looks like this. Here we see the intercept and age. So this stands for the beta naught and beta 1. Here are their values, or their estimated values. There's a lot of information given here. We'll talk about these results here in a minute, but what we want to look at right now are these last two results, lower 95 and upper 95. Those give us 95% confidence interval estimates of beta naught and beta 1. And so from these results here, we see that a 95% confidence interval estimate of beta naught is 64.3 up to 114.5. Now that confidence interval honestly isn't terribly significant, but the confidence interval for beta 1 is significant, is more significant. That confidence interval is beta 1 is somewhere between 0.137 and 0.976. So as indicated in the previous example, that the beta 1 or the slope is an indication of just how much systolic blood pressure increases for every 1 year increase in age. So based off of this, we would say that we're 95% confident that for each 1 year increase in age, systolic blood pressure increases somewhere between 0.137 and 0.976. So this tells us again approximately how much systolic blood pressure increases for each 1 year increase in age. Now we can also do some hypothesis tests about the values of these coefficients. So we're going to do 2 of them. First one is for beta naught, and here the null and alternative hypotheses are these statements. The null is that beta naught equals 0 versus beta naught is not equal to 0. And more informally, this hypothesis test, or the null hypothesis, is that the intercept is insignificant. If the intercept is 0, then that means we really don't need it, so it's insignificant. The alternative is that the intercept is significant. If it's not equal to 0, then that means we do need it, and so it's significant. And the p-value for this test is given here in this result. We also get the test statistic. This is called the t-stat, and here's the p-value. This is the p-value right here for this first hypothesis test regarding the intercept. And so this p-value is in scientific notation. The e-8 means it's 1.23 times 10 to the negative 8. Or in other words, it's a really small number. So we'll just take the p-values to be 0. We'd interpret that p-value just like any other p-value. We would reject the null hypothesis and in favor of the alternative hypothesis, and so we would conclude that the intercept is significant. It appears to not be 0. Okay. Now our second hypothesis test deals with the slope. The slope in this case is probably more important than the intercept, and so the hypotheses here that beta 1 is equal to 0 versus beta 1 is not equal to 0, or in more in informal terms, the null is that age is an insignificant predictor of systolic blood pressure. The alternative is that age is a significant predictor of systolic blood pressure. Here's the test statistic for that hypothesis test. Here's the p-value, and so interpret that p-value just like every other p-value. In this case, the p-value is small, meaning less than 0.05, and so we would reject the null hypothesis in favor of the alternative. And so we would conclude that age is a significant predictor of systolic blood pressure. So this kind of further confirms our suspicion that age is related to systolic blood pressure. This just confirms it in the form of a hypothesis test. Now let's look at another example of looking for relationships between 2 variables. And so this is example 9.2 from the Excel guide. And the question here is, does smoking affect systolic blood pressure? And so if we look at our data, this is the same data that we used in example 9.1. We have systolic blood pressure here, and then we've got smokes over here in this last column, where 1 indicates that the person does smoke and 0 indicates that the person does not smoke. In this case, smokes is what we call an indicator variable. Indicator variable means either its value 0 or 1. 1 means that that variable is present, 0 means that the variable is not present. Okay. And so we're going to answer this question in the same basic way as what we did in example 9.1. We're going to assume that in the population of all people, the variable of smokes and the variable of systolic blood pressure are related according to an equation that looks like this. And so, like in the previous example, we need to estimate the values of beta naught and beta 1. And we'll do that in the same way. Go to the Data tab, Data Analysis, choose Regression, format your window to look like this. In this case, the Y value or the Y range are the values of the systolic blood pressure. The X range is the values of smokes. Choose Labels. Choose any blank cell for the output range and click OK. And there are a lot of different results. Here in this case, let's focus in on just this set of results. which gives the values of our coefficients. So this is an estimate of beta naught. This is an estimate of beta 1. And so that would tell us that our regression equation is systolic blood pressure is our intercept plus our slope times the variable of smokes. And now if we look at the p-value here, specifically we're interested in this p-value for the hypothesis test about the value of smokes. So the p-value for smokes is 0.71, which is greater than 0.05. That's a rather large p-value. And so our conclusion would be to not reject the null hypothesis. The null hypothesis is the statement that that variable is an insignificant predictor of systolic blood pressure. And so in other words, smokes appears to be an insignificant predictor. So we would summarize that by saying that there is not a statistically significant relation between systolic blood pressure and smoking. We maybe thought that there was a relationship, but our data indicates that there is not a statistically significant relationship. So to kind of summarize these hypothesis tests that we do with the slope, the hypotheses are that the variable is not a significant predictor versus the variable is a significant predictor. If we get a small p-value, then we're going to reject the null hypothesis and conclude that the variable is a significant predictor. If we get a large p-value, we do not reject the null hypothesis and conclude that the variable is not a significant predictor. In this last example, we got a large p-value, and so we concluded that the variable is not a significant predictor. In the first example, we got a small p-value, and so we concluded that the variable is a significant predictor. So whenever you're reading a journal article, keep this in mind. You'll often see p-values for different predictor variables. A small p-value means that that variable is significant. A large p-value indicates that that variable is not significant.